Awesome. It's a pleasure to be here with everyone here today. My name is FWAM Scoullos. I'm a senior solutions architect at NVIDIA. I work on the financial services industry team. A little bit about myself. I've been at NVIDIA close to 3 years. Prior to that, my educational background is I did my undergrad at Rutgers in chemical engineering and then my PhD at Princeton, also in chemical engineering. While at NVIDIA, I've been focusing quite a bit on large language models, and recently was involved with Bloomberg GPT, if some of you have heard of that particular model, and helping Bloomberg, as my particular customer in financial services, help train that model and get over the line. And a lot of current work for me right now is involved with training really long context large language models for a number of financial applications applied to tabular data. So for today's talk, I'm going to provide 4 areas, although I anticipate probably only getting to the first 3. And I believe you'll have access to the slides later. So feel free to email me. My email was on that first slide if there's any particular questions. And so the aim for today is to give some high-level background into GPU acceleration. Then we're going to discuss 5 ways to accelerate with GPUs. And then I'm going to actually dive into a real example on accelerating option pricing portfolios with standard C++ and show some of those tools there. And then, like I said, time permitting, we'll dive into some of my recent work using large language models. So acceleration for large-scale quantitative workflows, like someone caught the joke here. This is your workflows today. Your quantitative workflows are not your PhD, your advisor's GPUs. The goal for today is to provide some hands-on examples for how to leverage modern acceleration capabilities to improve on your existing code bases. And so your PhD advisor may have written some low-level code in C or C++, maybe had separate code bases for CPU code and GPU code, probably wrote some algorithms from scratch, maybe because they didn't exist at the time in other libraries, or if they're a little bit more recent, maybe use some Python. And after this talk, I'm hoping to show how you can use OpenACC or even ISO C++ 17 or higher for thinking about your code bases in a parallel first fashion, using a single code base for CPU and GPU code and just compiling to the particular architecture that you need. Leveraging NVIDIA SDKs as well as Docker containers that you can pull for free, and rapid prototyping using accelerated GPU accelerated Python. So when you think about accelerated computing, it's both the conjunction of CPU and GPU work. The CPU, as most of you know, is optimized for general purpose computing. It's and specifically for serial-like tasks. And the GPU is optimized for parallel tasks, since it essentially has many, many more cores than a CPU has. Okay, and so when you think about your code that you have maybe in your current workflow, you'll have 5% of your code that might be really hot with a lot of compute. You have probably, some for loops or nested for loops where you're really running some function and you're doing some very heavy calculation in there. And then the rest of that is some serial or sequential code. And so the idea is that when you have this kind of code, like if you're doing molecular dynamics or some other kind of code, the sequential code really belongs on CPU. That's where it will, probably do better. And the GPU code will be more amenable for that heavy compute task where you'll have those for loops that could be parallelized. And so the GPU architecture has 2 main components for this kind of acceleration. One is global memory, and the other one is streaming multiprocessors. And so At a high level, this global memory is analogous to RAM in a CPU. And this GPU RAM is accessible by both GPU and CPU. Our latest H100, our Hopper GPU, has 80 gigs of RAM, for example. SMs, on the other hand, streaming multiprocessors, actually perform the calculation, and each SM has its own control units, registers, execution pipelines, and caches. And H100, our latest GPU, has 114 SMs. And usually, as generation over generation, the number of SMs tends to increase, and enabling even more throughput and processing of workloads. So for GPU architecture, going a little bit deeper into SMs, there are many CUDA cores per SM. And this is architecture dependent, but in H100, each SM has 128 cores. And so if you look here at the bottom, you have 14,000, let's call it 14,500 cores. So it's basically 128 times the 114 that you saw on the previous slide. Each SM also has some special functions like cosines, sines, and tangent that allows hardware acceleration for those workloads. And within each SM, the cores also share some memory via the L1 cache. And so you have also these 32-bit registers. The memory hierarchy, thus, if you think about it, it starts with global memory, then there's an L2 cache, then there's the shared memory plus L1 cache, and then those registers. And so with the processing flow for that application that we saw in the beginning, where that 5% would run on the GPU, that hot workload, I'm going to kind of show you what that looks like from the hardware perspective. So what you'll first do is you'll have some array or something on your CPU memory. You're going to do a copy to the memory on the GPU. And by the way, I will note here that bandwidth, that speed of that copy is limited by the PCIe bus. And so one thing that NVIDIA has, so there's different formats of how you can transfer the data from CPU to GPU. One is PCIe. NVIDIA also has developed another, if you will, technique or interconnect called NVLink, which allows even faster transfers. And for our latest Grace Hopper GPU, it's 900 gigabytes, not bits, gigabytes per second bidirectional bandwidth for transferring data. So if you're really doing a lot of number crunching, that's where you're going to see dramatic benefits compared to PCIe or even such as PCIe Gen 4.
Can I ask a question about what you just mentioned? I mean, so I'm slightly out of date, and we wrote a code that used, and we had this limit of like 48 kilobytes shared memory per core. Is that right? Is that still about right when you were talking about shared memory?
I'm referring to, so you're probably getting closer to like maybe the memory per SM, but that's still a lot smaller than I think what you could do today. Yeah.
Okay.
See, that could be something for optimizing, and certainly we could set something up with Ronak, and Ronak is the account manager. You could say, hi, Ronak, a little bit later to dive into that.
All right, just to get the specs. Okay, thanks.
Mm-hmm. And so afterwards, so you've loaded your arrays or other kind of data. Now you need to also load your kernels, your functions, essentially, from the CPU onto the GPU and run them, right? And then you can actually cache that particular data onto the GPU if you need to use that again and again and again. And that's primarily for performance reasons. And then when you're done, you'll copy your results back from the GPU back to the CPU to continue on in that sequential workflow. Okay? Now, this is all enabled by NVIDIA's CUDA library. And for those that aren't familiar, NVIDIA's CUDA stands for Compute Unified Device Architecture. And it's a parallel computing library and platform and application created by NVIDIA for software engineers and quantitative developers to accelerate GPU workflows. And the other cool features about CUDA is that it's backwards compatible. So if you're using, if you have a CUDA version of 12, which we are at now, but you wrote your code for 11, a lot of times you could just recompile it again for CUDA 12 without making any code changes, and it'll work just fine. There's also minor version compatibility in CUDA. So if you're using CUDA 11.1, and now we have 11.8, you can also bump up within a particular CUDA version. So all of this is enabled through NVIDIA's high performance compute SDK. It's available as a container on our NGC, which is NVIDIA's essentially Docker repository. You can also get that in the cloud if you're using cloud compute, and it comes for free. Everything you're seeing here is for free. So starting here on the left is with our programming models. It comes with standard C++ and Fortran, OpenACC and MP, as well as CUDA. It's also provided compilers for free as well. So NVCC for CUDA compiling, NVC for C code, NVC++, and NV-Fortran. It also comes with libraries like libq-C++ and Thrust. Thrust, for example, is a library. You can even get that on GitHub if you want, for parallel algorithms and data structures. There's also free libraries for free math libraries. So cuBLAS, probably some of you guys may be familiar with just other basic linear algebras. cuBLAS is the GPU accelerated version. cuTensor, et cetera. cuRAND, for example, does random number generation on GPUs. And cuFFT, for example, for signal processing workloads. And not to also make sure I forget these communication libraries, such as MPI, NVSHMEM, which is NVIDIA's shared memory protocol, as well as NCCL. And NCCL is NVIDIA's communications library. And these libraries enable very fast communication between CPU to GPU, as well as GPU to GPU, and then GPU to GPU in another node or another server. And that's important if your workloads are really spanning multiple servers. And it's a key component of training, especially large language models where they're using thousands of GPUs. And you need to maintain performance as you do things like all reduce functions. And then lastly, the HPC SDK comes with Nsight systems and compute for profiling, as well as debugging. And so all of this is for free. It's all cross-platform. You can use it on x86, you can use it on ARM and OpenPower. And of course, you can use it to compile to our NVIDIA GPUs. And so the aim is really to help open up the community by showing all these tools here that can be used for your particular accelerated workflow. So now we're going to dive into 5 ways to accelerate your workloads with GPUs. So there's, as with many things, there's kind of a spectrum of ways to accelerate your workloads. And they vary in terms of the amount of flexibility that they provide to the end developer, which is yourself or your team, and then with regards to accessibility. And so if you start here on the left-hand side, you have applications. So this is essentially, like we're saying, getting straight to the science. You're using a platform for doing your workloads, and there's not much configurability necessarily because you have to follow the specifications within that particular application. Next, you have libraries which aim to provide drop-in acceleration. For example, replacing one function with another function in like, for example, cuBLAS, our math library. Next, you'll have OpenACC directives, which allows you to also accelerate applications, and provide compiler hints to your source code to parallelize compute-intensive loops. Next, you have CUDA programming, which definitely will provide you maximum performance, but will certainly require quite a bit of of tuning and learning that particular language. And then lastly, of course, you have standard language parallelism. Think of ISO C++, Fortran, et cetera, which really provide you the maximum flexibility and allow you to customize particular components for your application. And so the neat thing about all of this is that every one of those components can actually work independently from one another in your application. So you can use Scoullos as a library, and then if some particular kernel is not there, you can code it up yourself and use that kernel within your own application if you're doing some groundbreaking research. So I'm going to focus now on applications, and then we're going to work our way left to right. And so there are thousands of GPU accelerated applications. NVIDIA is not just gaming, folks. It's not just molecular dynamics simulations or other things. NVIDIA is truly involved in every single industry. For example, artificial intelligence, using PyTorch or TensorFlow, for those that like to use those libraries, like myself. Climate and weather, computational finance. For example, even the life sciences, these are a lot of molecular dynamics codes or DFT codes for density functional theory. NVIDIA accelerates it all. Even for your particular workload, you may have an application that is already GPU accelerated. And so something to consider for your particular workload is using an already GPU accelerated ones. Many of these, we have containers on our NVIDIA Docker repository, NGC. Go to ngc.nvidia.com. You could pull the container. It has all the dependencies in there. For example, even things like VASP or LAMPS or NAMD. And even PyTorch. And so you can use that, have all the dependencies managed for you so that you don't have to think about, oh, I forgot to install this library, and oh, I forgot to install this one or upgrade this one and manage this one. And use the Docker container to help you accelerate it all, okay? So just to think about some standard benchmarking, I have here just a list of just some HPC applications. For example, a lot of these top ones are molecular dynamics codes here. Chroma is a cryo-electron microscopy code, and there's some other ones here. And you see that you're seeing a lot of speed ups here ranging, 4 to even like 30, 40x over a dual socket CPU. And that's with one single A100 GPU, which A100 is our last generation GPU. And that's one of them. And typically in a server, you might have 4 or 8 of them. And then, of course, it doesn't also preclude you from doing multi-GPU on multiple servers, which would even further compound the parallelization opportunities here. And a little personal note here. So like, as I said in the beginning, I did my PhD in chemical engineering. I actually had some collaborators doing some DFT, some density functional theory work. And back when I did my PhD, and as you can tell, I'm not the oldest person in the room, that DFT simulation took like a month and a half easily on CPUs. And to think how today, just a short few number of years later, I don't have that much gray hair. That DFT work would have actually been done in a single day. And so that really, think about it, not just as the time, but as the iteration time, because many of you folks are researchers. I have come from a research background. You're not just doing one experiment, you're going to do multiple. You're going to say, oh, well, I made this mistake, or, oh, and now I need to change this configuration, or move this atom or molecule here and there. And so think of it as the productivity benefit for the speed up, not necessarily the speed up due to timing there. It enables you to do more research and more effective research. And that's where really you should be inspired for using GPUs. Here's some other sample applications. You're probably even using some of these today. I know I'm a big user of PyTorch for a lot of the large language model workloads, and as well as MATLAB, Mathematica, et cetera. Some of these other ones are for CFD simulations, et cetera. So I'm probably using them. Try to use the GPU accelerated version. And I'll try to remember to touch on some PyTorch stuff when we go over some profiling a little bit later. Making sure to mention that. Next, we'll talk about some libraries, which the aim here, again, is to provide drop-in acceleration. And so the aim for these libraries is ease of use, again, drop-in acceleration, quality, and performance. Okay, so these libraries, the aim is to be ease of use, right? They're not aimed to be super complex. You don't need to know the specifics of CUDA to use these libraries. And so that, as a result, enables them to be dropped in. If you're using a particular kernel, you could drop in the CUDA equivalent and get the acceleration benefits. In addition, it's quality, because NVIDIA libraries are offering a number of implementations for a broad range of applications. And then lastly, performance. NVIDIA, we have a team, an army of NVIDIA CUDA experts that think about CUDA every single day and how to accelerate things, even in some cases writing assembly code to get the most performance out of particular functions. And so you may as well use the library function because it'll be much faster, likely, than something that you implement yourself. And of course, if it's not there, there are other parts of that workflow I showed you, those 5 ways, that you can still incorporate your own functions. And so the other last thing to say about performance is that one neat thing about NVIDIA GPUs is exactly the performance. The library, as you own a GPU, so if you have an A100 GPU, as you own it, that library that you're using, cuBLAS, we're picking on cuBLAS today, that library gets improved over time. And so your GPU actually gets faster over time. All right. And so we're seeing that sometimes in certain applications, like especially for a lot of deep neural networks, you can actually get 2x the performance over the lifetime of the GPU just by using the same GPU, but updating the libraries. So really think about that component of these GPU accelerated libraries. And so what does it look like? We're going to look at brief Saxby example. That's single precision A X times Y. So here's the CPU call, and here's the equivalent CUDA library call, right? And so that's what I mean by drop-in replacement. Now you may have to also manage data locality. So you have malloc or CUDA malloc here and CUDA memcopy to help copy that data from CPU to GPU, as we showed in that initial diagram earlier. And sometimes, by the way, this step is even done in the library itself. And then lastly, you can rebuild and link the library to your CUDA accelerated library. And that's basically it. And you can take advantage of CUDA accelerated applications. So here's a not comprehensive list of GPU accelerated libraries. We've been picking on cuBLAS today for basic linear algebra. I talked about cuFFT for signal processing and cuRAND for random number generation, and the list goes on. There's even Thrust, for example, as I mentioned earlier, for C++ parallel algorithms and data structures. NVJPEG, if you're dealing with images, you can actually load images easily onto GPUs, and so on and so forth. And so there are a ton of libraries. We provide a CUDA library, samples, and there are examples for how to use this code so that you can integrate it into your application and research. Now, as we transition over to the Python ecosystem, Numba, for example, is one library that you could use to accelerate your work. Actually, NVIDIA, the person who developed Numba actually works at NVIDIA. And so it supports CUDA GPU programming by compiling a restricted subset of Python into CUDA kernels and device functions, device meaning GPU, following the CUDA execution model. And typically you use that through Python decorators, like @JIT for just-in-time compiling, or CUDA JIT if you're going to do CUDA-based compiling. And then this vectorized function actually allows, this vectorized decorator allows taking Python functions, taking scalar inputs, and being used as NumPy ufunctions. And so Numba is certainly something to consider. But I tend to, yes.
Can I ask, given that your data is sitting on the CPU, the regular CPU RAM, how does every little number function that's compiled this way do host to device transfer and back each time, or how's that?
It'll handle that for you, yeah.
Is there a way to sort of do it so with numbers so it all stays on the GPU, or, no, or maybe that's
Um,
a detailed question. But
That's something I'd have to think about
yeah,
for staying on the GPU. Yeah, that's a good one. I don't know that one off the top of my head.
because you only get, because that can, yeah, okay,
Um,
thanks.
yeah, when I've used Numba, it's not for super long-lived kernels where you're going to have data persisting on there. CuPy is one of my favorite ones, actually. Personally, a little bit more than Numba. CuPy is another GPU accelerated library. Think of it as NumPy, but on GPUs, hence CuPy. It's basically meant to be a drop-in replacement for CuPy, for NumPy and SciPy. So you can basically replace NumPy with CuPy, and then you can basically replace SciPy with CuPyX.SciPy. And you can speed up a number of these applications more than 100x. So as you see here, especially as your data set size increases, if you focus here on the purple for the particular kinds of calculation you're doing, like singular value decomposition, you can get good 10x or so, a little, like, call it 15, 20x, maybe 17x performance over using that same thing on CPU. Personally, I like using CuPy, and one example where I've used it recently was I had an embedding matrix. So I had a basically, matrix, and I wanted to do cosine similarity of every row against every other row. And it's just a ton faster than using NumPy for a lot of those. Yes.
How nicely does that degrade if your code is going to, you don't know the system that you're going to be running on, whether GPUs are going to be available? Do you have to manually check what libraries are available, or does it just degrade to?
So the question, so CuPy expects GPUs to be available. So it will, when you import CuPy, it'll check that you have even like the CUDA driver loaded. Yeah.
Does that mean you have to maintain over code based on what libraries available, or?
In CuPy land, yes, you would. Yes. We'll talk about C++ later, which you don't. But of course, Python, a little bit easier to code. C++ takes a little bit more thought. But yes, that's certainly one thing to think about. The other area is with Rapids. So again, yes, you will need to have GPUs for Rapids. I like using Rapids for a lot of my daily workflows. Rapids has a number of these libraries here. Just going to focus here on cuDF and cuML. cuDF is essentially pandas, but on GPUs. And so if you're doing anything over like 100,000 rows or more of data, you want to be using cuDF and getting a lot of acceleration benefits. GPUs are super fast, even for things like group by operations. GPUs can parallelize all that. And so you should be using GPUs for this kind of workload. cuML is the analog for scikit-learn. So all of your scikit-learn APIs and algorithms are available to be GPU accelerated. And then there's all these other ones, cuGraph for NetworkX-like things for folks working on graphs or heterogeneous graphs as well. And so just kind of highlighting some of the things in cuML, it really spans the gamut. If you have things like decision trees, random forest, linear regression, k-nearest neighbors. I don't have XGBoost here, but it's there too, GPU accelerated XGBoost. If you're doing any sort of text work, we even have GPU accelerated, TF-IDF, cross-validation, et cetera. Any clustering work, if you're going to do, PCA, k-means, et cetera, is available. Some visualization work with UMAP or tsne is also available to be GPU accelerated. And if you're doing things like UMAP, you probably want to be using GPUs because it will dramatically accelerate up your ability to calculate things like UMAP on some large data sets. If you're doing time series work, there's also GPU accelerated Holt-Winters or ARIMA models. So that's your autoregressive moving average style models, as well as things to do cross-validation, hyperparameter tuning, your train test split, et cetera, is all available to be GPU accelerated. Yes.
Does this follow the API for scikit-learn, for example?
Like exactly. Minus the import cuML part. It's exactly, yes. So now kind of as we're moving more towards the flexibility, we're going to be talking a little bit briefly about OpenACC directives and how they can be used. So OpenACC is this user-driven directive, call it language with quotation marks, if you will, because we're using directives. It's really designed for scientists and engineers that have existing code bases that they want to accelerate without necessarily thinking about all the ways that they need to accelerate using CUDA and C++. And so you essentially provide these directives here. For example, you provide these pragmas, ACC directives, and it's often followed by a for loop or double for loop or other kind of nested for loops that could be easily parallelized, other kind of hotspots in your code. The Fortran version is of that same thing is shown here, where you have to essentially bound it with this directive and then the end directive. And that these provide essentially compiler hints for doing this work. The compiler will parallelize the code, and it also the nice neat thing is that it works on many core GPUs and CPUs, and so it's really the easy way to get really fast acceleration on CPUs and GPUs. And so really that workflow involved with using OpenACC, as well as all the other stuff we're about to be talking about later on in this talk, is to identify available parallelism, express it. Sometimes we need to express this data movement because OpenACC doesn't do that by default. And then you can optimize the loop performance by providing those directives over your particular loop. So keep this paradigm in mind, because this is going to show up a little bit later when I provide the ISO C++ examples for option portfolios. Okay, the same paradigm is still there. This is also part of our GPU hackathons. Yes, so we can. Yes.
So just to follow up on something you just said, so the code assumes the data is sitting on the device, on the GPU now.
No, it does not. It assumes a CPU, for example.
CPU. Okay. So it does do it'll move it over. If you have like a expensive loop.
You, the user, would need to move that over.
You move it over. Yeah. Okay. Right. Okay. So you can write code where everything stays on the GPU this way.
Mm-hmm.
Right. Good.
Sure. So OpenACC is pretty popular in the scientific community. About 400 applications have already been ported over in part or completely to GPUs. And so there's a number of domain experts at many research institutes, such as yourselves, as well as other universities already using OpenACC. So looking at that Saxby example again, here's Saxby here in C, where you're seeing there's your A times X plus Y. And here's that pragma ACC kernels bound with those braces here. And we're basically telling the compiler that we want to parallelize this loop because basically we can compute all of these calculations in parallel for that. And you see here the way that we'll call that here with that particular function. And so same thing, same idea in Fortran, where you have those loops. And like I said, what you're basically telling the compiler to do is to parallelize, let me find my mouse, there you go, this section of the code and run it on the accelerator. So some applications already using OpenACC, some of them you may be already using. Just highlighting some of the list. Again, I'm going to pick on VASP for DFT style codes, or if you're using other kind of molecular dynamics codes, as well as some other ones. And so there's a number of these applications already using that and seeing the benefits of acceleration on NVIDIA GPUs. So next, we'll move over to CUDA programming, which really the aim there is to offer maximum performance for your particular workload. And so, excuse me. CUDA gives you fine level control over thread execution. We talked about that memory hierarchy. It allows you fine level control over those. Of course, you could tune it to your particular level of performance and scale it across multiple GPUs using nickel and MPI. And so you as the programmer have control of how that data is moved to the GPU and back, how that shared memory and cache on the GPU is utilized, and how and where those threads are run. CUDA is also available, as you saw, for a number of languages like C, C++, Fortran, Python, etc. So let's just look here at this C example here. And so you see this is that Saxby example we've been looking at a number of times. And you're seeing how we're doing this particular call on roughly 1 million elements here, where we're iterating over each and doing this particular computation. When you try to move that over to CUDA, you're going to first see this global here, which global tells you that this is going to be a device function, device meaning GPU, not a host function. Next, you'll see here this block index, block dimension, and thread index. Those are built-in variables in CUDA, and that tells you how that computation is broken into the threads, and each thread is included, is executed in blocks, and it's all executed in parallel. And you notice a slight difference here is also in this if statement here, if I is less than n. And that's essentially saying the index of that particular thread, we want to make sure that we're less than the number of elements here so that we don't get a memory out of bounds. And then lastly, you're seeing this, this execution here, where we're having the number of blocks and the number of threads here with these triple braces. Excuse me, there we go. And essentially you can run that and run all of these, run this calculation entirely in parallel on a GPU. And so every thread is working on computing one element in that array. The other library you can use is Thrust, which is another interesting C++ library. It's all offered in the HPC SDK. It resembles C++ STL. It has a high-level interface to enhance your productivity. It's flexible and powerful as well, and enables highly efficient GPU code to be written. So if you look here, you have this host vector here. Then we're going to be generating some stuff into this vector. We have this beginning and end, which is some nice metadata in there. And then we're going to transfer this to create this device vector, which enables transferring the data to the device. In this case, we're going to do some radix sort of on this particular vector, and then transferring the data back with thrust copy here. So it's a really nice API and to enable your particular workflow. Lastly, CUDA Fortran. Quick hand raise just to do a temperature check on the audience. Who writes in Fortran every day? Every day. Okay, so this slide is for you. So I'm going to keep my hand down for that one. There is CUDA Fortran to accelerate those particular workflows. Again, all these simple extensions here in this example, you have again the thread index, block index, etc. For computing that, and you have this execution configuration shown here for the block and the thread. Again, running those roughly million threads for this calculation. There's a number of developer tools. We talked about that a little bit briefly earlier. Nsight Systems is awesome for looking at your overall application, creating profiles of that. I recently did that with a particular big bank to profile some workloads for them. And there's also some IDE plugins too. If you're a VS Visual Studio Code developer, you can use those particular plugins. Yes.
For the two examples you just showed, did you leave out something about moving the data back in and out, or Was that just automatic somehow?
I was leaving that out. Yeah, I wanted to focus more on how you would write those device functions and actually execute them. Yeah, so you will have to do some memory allocation on the GPU. That's correct. Okay. All right. Now we're going to talk about our standard language parallelism. And we're actually going to spend quite a bit of time on this, going into the actual practical examples a little bit later. So NVIDIA Accelerate, and this is actually honestly one of the biggest takeaways. I'm going to say it now and I'm going to say it again later. One of the biggest takeaways I want you to take away from this presentation is that you can now code in ISO C++, Fortran, and even Python for certain things. We're going to focus today on C++, and then compile to the particular architecture. You see, you're basically doing the same thing here, that Saxby style kernel on CPUs, in C++, Fortran, and Python. And then the only difference here, where I'm just showing C++ and Python for now. For CPU, you would take that same code, compile with C++, and put this the standard parallelism here for multi-core. And for Fortran, that's what you would do. For GPUs, it's the same compiler. You just specify you want to be using GPUs. And honestly, this is one of the awesome benefits. It allows you to have one code base, and compile to the architecture that you want. Okay. You can compile, basically write once and run essentially anywhere because we're using x86, ARM, et cetera, CUDA. Yes.
For this, for a given program, can you then only have GPU parallelism or CPU parallelism? Or I guess I'm not understanding, like when you do STD par here for multi-core and GPU, do the GPU one turn off any automatic parallelism for doing CPU stuff? with STD transfer?
That's a good question. I don't know that one off the top of my head. Usually we're just using it for GPU parallelism, not simultaneously. My guess is yes, though.
Okay.
But the short answer is I don't know, and that's something we can get back to you on.
Okay.
But that would be my hunch. So let's look at one particular application here. So Lulesh is a hydrodynamics code. It's written in 9,000 lines of C. It's a stress compiler vectorization designed to stress compiler vectorization, parallel overheads, and on-node parallelism. And so let's just look at what that code porting would look like. So it's a little bit hard to see, but we see that this code was originally written with this OpenMP directives here. And when you write that in C++, you could see first thing you notice is obviously a lot less code. And then the next thing you see is that since you can compile it to different architectures, you can get speed ups depending on, again, what you're using it for. And then the other second thing there is less code equals hopefully less bugs, or less silent bugs to find. And so that's a huge benefit. And so let's look at the performance there. If you look at the OpenMP example, that's a reference base of 1 on 64 cores. Just using the NVIDIA compiler gets you, again, basically the same benefit. And when you use ISO C++, you actually get a little bit of a performance improvement over OpenMP, just happened to be so in this example. Compiling actually doubled that performance. And then, of course, using that on GPU, you get a much greater performance using this ISO C++. Just taking that same exact code. And here is the same exact C++ code. So if you have C++ code, particularly C++ 17 and newer, you can compile with NVC++ to your desired architecture. So that's essentially it with the 5 ways to accelerate GPUs. I'm going to now dive a little bit more deeply into option portfolios in standard C++. And if you're not a finance person, that is totally fine. You don't need to know any finance for this particular application. We're just going to think about coding in a parallel manner. Okay? Yes.
Before you get So that, I mean, you showed two things that look very similar. That's Open ACC, which has, directives just before loops. And then you showed this last, like, C++ language parallelism, which also has a pragmas just before loops and things. Is that it?
Well, that was for the OpenMP example. So the idea with here was to say,
They're the same. I mean, like, is there a way to explain the difference between those two?
so OpenACC is using those directives,
Yeah.
and ISO C++ is standard C++. And so in the standard C++, now you're just having the compiler do the optimizations for you on your architecture.
Oh, I see. So OpenACC, you don't write. It's not decorating C++ code. It's its own language.
You're kind in the Python sense. You're like decorating for loops, if you will, where you're providing those OpenACC directives over the for loops, and you can do things like collapsing a nested for loops to be run in parallel. So the aim with OpenACC is not much code change to your existing code. With ISO C++, or ISO C++, the aim there is you might need to actually do a little bit of modernization, provides more flexibility, but you can actually get those performance benefits.
Okay.
So OpenACC is great if you have existing code, definitely. And or like, million lines of existing code that you don't want to actually go through and rethink and parallelize. And as we're all seeing GPUs get more and more powerful, there's going to be a little bit of a paradigm shift. So I'm going to say it now, and I'm going to say it at the end of this particular section, just to kind of get your minds thinking. When you all learned to code, your first thing was, how to assign a variable or maybe printing a hello world. And then the next thing you did was write a for loop, right? And that's because really at the time, CPUs were good enough, they did the works okay. But now that GPUs are so fast, so powerful, you really have to rethink your paradigm. And instead of when you're writing an application, it almost requires a little bit of retraining. You need to code in a parallel first manner. And you're going to see that theme pop up. I'm saying it now, I'm going to say it a little bit later. Okay. So code in a parallel first manner, that's where ISO C++ is going to be super beneficial. Okay. So again, now we're going to talk about HPC's programming in ISO C++. C++ has a long pipeline supporting parallel programming. It actually technically can, if you think about it, could go all the way back to C++ 11, but we're going to just talk about mainly C++ 17 when the parallel algorithms library began to be supported here. And so the examples today will show how the parallel libraries, these parallel algorithms can be used, parallel algorithms library can be used to build parallel code. I'm going to also point out here this MD span available in C++ 23, which allows these multi-dimensional array abstractions. When you use MD span, it actually will inject some metadata in there, which provides some nice convenience functions. So that's going to pop up in today's example. And then also just want to highlight senders and receivers, which is in C++ 26, although there's actually a preview available now. And that's a standardized way of representing asynchronous work. Essentially, you can have a task graph that runs things, kind of addressing your question. Some things can be on GPU and other things can be on CPU. And for things like our Grace Hopper architecture, Grace is NVIDIA's CPU, and with Hopper being the GPU, you can now have those task graphs running things asynchronously on both. So just to kind of make your mind be thinking about those. So for today's example, there's two examples today. We're going to be focusing on the first one here. First, let me take a step back. Option portfolios. Who understands a little bit what options are in the market? Okay, great. So you don't need to know anything about options. But so today's focus is actually going to be looking at vanilla options. And if you have for example, a large portfolio of options to manage, it could be various different asset classes like equities, currencies, et cetera. This can cause a nonlinear PV function that evolves over time and it lives in a high dimensional space. And so options basically have a time before they expire. And so as time progresses, the options move in and out of the money. And as this expiry gets shorter, there are thus these portfolio dynamics that evolves. And every option lives in its own volatility space. Volatility, if you don't know what it is, basically think about it like standard deviation in finance terms. Also, since we can't predict the future, as we all like to do, we like to explore multiple hypotheses, multiple plausible scenarios using simulation. And in the past, because this was in a very expensive computation, you'd have to do things like calculating expected values or making other kind of simplifying assumptions. But today, with the GPU power being so great, you actually don't need to do that. You can actually calculate the full profit and loss distributions based on that. And so that allows also, if you're working at a hedge fund, it allows new strategies to be explored as well. And this is all within the context of portfolio optimization, where you want fast calculation of PV and Greeks. So in this first example, that you have this fast PV in Greeks, it's a massively parallel problem here. And the goal is to offload those parallelizable workloads onto the GPU. In this case, we're using a Black-Scholes model. Something else can be chosen, something more advanced, additional parameters, but we're just focusing on a simple Black-Scholes model today. And we're using a large grid of options here with different maturities, volatilities, and strikes. And so you basically need to compute a very large grid of these things. And so this is awesome for using GPUs to parallelize this kind of simulation work. And then in the second example, we're going to essentially consider a basket of these options now. And so you're simulating the profit and loss of this large universe of options. And in this case, this grid of call options you have a grid now of call options of various strikes and maturities. There's something called delta hedging, which basically if you're a market maker or a vol trader, you're going to take that kind of perspective. And we want to simulate this P&L distribution in n time steps with m different paths. So if you look here, this daily P&L is a sum. So this is the daily term essentially in the sum from I to n-1. So this is essentially one particular day. It's this balance from this gain and then this loss due to theta here. And then so if the underlying asset using the option moves a lot, then this gain in gamma can offset the particular cost. Then opposite days can cause the P&L to actually be negative. And so doing this over and over with that basket of options is now possible in real time. So I'm showing you here a grid of particular options here. You have moneyness in percent here on the x-axis, time to maturity on the y-axis, and then the color is the P&L. And this is just a 3D view of what that surface would look like. And you're seeing, here just a sampling of some of the path. Every cell in this grid is an option with a particular maturity. And then that color, every path here, as you see, is a total of 30 days, this difference here. And so it's a very compute intensive calculation to do this, not just for one option, but a bunch of them. And if you're going to do something more complex where you're adding additional terms, maybe slightly different models, this thing gets really, can get unwieldy pretty quickly. And so here's the exact example. And so for all those folks that don't know Black-Scholes, the best part is you don't need to know Black-Scholes. So everything about Black-Scholes is in this function called Black-Scholes body. And so that's great for folks that don't know Black-Scholes, and that's also great for folks that know Black-Scholes because they've probably already coded it and they don't need to see it again for like the 10 billionth time. And so I'm showing you here an original baseline. It should be familiar with what I was just describing here. We have a 2D loop, if you will, this nested loop here with OpenMP. you're iterating over the Greeks as well as the number of options. And then we actually have to create this index and then calculate our Black-Scholes model here. So it's CPU parallelized here with these OpenMP directives. However, it's OpenMP is fine for running these multi-threaded workloads, but to move it to GPU will require some fundamentally different paradigms. And so we'll see now how do we move this into parallel C++ features to modernize it for GPUs. And so the aim here is to show that there won't be a whole lot of code changes, okay, in this example. You really should be focusing on these for loops and how that's going to be changing, okay? All right, so here's what we're doing. So for all this new code, not a whole lot has changed. You see, we still have our Black-Scholes body here, all right? And then so, although strictly not necessary, here in one, we're using C++ spans. It's that idiomatic way for passing views into your data. We're also using this array view, which will pop up later. This is just an example of a two-dimensional MD span. That's just what we called it. You can call it something else. And this will be discussed a little bit later. This iota here in two, in this part two, ranges essentially from 0 to this number of options times the number of Greeks. And this generates that range without storing -1, excuse me, 0 to this number -1, of course. And this generates all those things without storing every value in memory. And then we use for each from the parallel library to essentially replace the for loop. And then we're calling standard execution with par on sequence here, which tells to the compiler that this for each can execute in parallel and end in any order. And then as you see, the bulk of the code is still in the Black-Scholes body. We've now had to do some actual indexing here. It's actually in a way like almost like the reverse of what we just showed with regards to indexing, where you have to calculate it yourself with manually here using this particular thing. So the indexing is slightly different here. But simply just modernizing this sequential double for loop into this parallel algorithm actually can get you some performance benefits. And so if you're looking at this whole presentation so far, here's that example before and after here, where we're removing this, putting this side by side. We're not writing any more code here. We removed this OpenMP. We've collapsed these for loops into the for each. We're now doing a views, this iota function. This iota here. And then the only difference here is really that indexing. And so if you have a lot of code written in C++, before C++ 17, or even, other example of code, and everything so far in this presentation has seemed daunting, here's another alternative for you. You can actually do that and get some decent results for helping you write your code. And so we actually asked ChatGPT to convert your code into a parallel one in standard C++ here. And let's see how well ChatGPT did. So that's actually the answer here. You can see that. So the idea here is that you can actually see that these large language models like ChatGPT can be actually useful for modernizing your code base and augmenting your work and providing productivity benefits. So use these tools for that purpose. Make you an even better developer than you are.
So, I mean, for me, readability is the thing that is totally lost in these modern C++ constructs. So, I mean, what I want to do is take that code and convert it into a code I can read. I assume you could probably do that with ChatGPT too, right? But I mean, I think, are we never going to look at for loops that go from I as 1 to n, even though, and it's all going to get replaced by this, standard execution for each type stuff, because it's supposed to be asynchronous. Is that? Because we don't like the for loop looking serial in some way.
Well, so that's the best part about C++ is that you're still allowed to write for the old school way. You're gonna, we're talking about really squeezing extra performance out. And when you squeeze that, and as I highlighted earlier, squeezing extra performance out means you're able to iterate more, do more experiments, and hopefully get your results faster, publish faster. It's a cascading thing, and that's coming from, again, my background as a researcher. And by the way, that iota actually, where you saw that actually reminds me more of like a Python range, for I in range is, by the way. So actually, I like that one actually.
Use this versus just taking my Pragma and using OpenMP with GPU, because they have GPU support now. And it's not bad. It's pretty much on par with OpenACC, and so I can just change one line of code,
Okay.
right?
So you'll see that a little bit later when, because what I said at the beginning of this section was think about coding in a parallel first manner, where some of the existing code, when it was written, it was not coded in that way. And you're going to see in the second example that we're going to get to in a moment, where trying to do this for each is, you would think is a smart way to do it to get the best performance, but it's actually not. So I'm gonna, hopefully that'll address the answer to your question, where doing that, again, will get you somewhere. It'll get you faster, but it's not actually the fastest that it really could be. And so you'll have to evaluate for yourself. Is that good enough? Maybe that's good enough for this year or next year, but is that good enough for the year after that? And so that's something to continue to evaluate. It pops up a lot in the customers that I see where they have code written for GPUs that's like 10, 20 years old, and more like 15, I would say. And it ends up being that there's like a technical debt that keeps on accumulating because there's no effort to try to modernize. The other benefit, as you're seeing here, is also you can write in C++, and we're talking about compiling it to the particular hardware, which is nice to have one single uni repo, if you will, or mono repo. And so here's the actual comparison between ChatGPT and what we had. And you see basically it captured a lot of the same ideas here, where you have your IOTAs, you have your for each with standard execution par, and they even did the indexing correct as well and maintain the Black-Scholes body. I'm just offering that as another additional technique for you to try and maybe help, with some of the boilerplate code that you have. Yes.
Question. In your lambda, one's captured by copy and the other by reference. Which one is correct?
Probably ours.
But that means that the ChatGPT is wrong, or what?
But it's not bad. I mean, it gets you pretty close. The idea is, I mean, if ChatGPT wrote this all in a second, you didn't have to actually think about it. You picked out that as an error, that could be an error like right away that you pick out and that you'd fix. But you didn't have to write all that. That's something you can copy paste, and then you look at it and you'll say, oh, that's maybe needs a fix. That's fine. At least you didn't actually have to think about all that API right away.
Except if you have a crash that you need 30 minutes to find.
That again?
Except if it crashes, and then you have to find it.
Fair. I mean, if you're copying code and that's like copying code from like on the internet and expecting it to, I mean.
Correct. It's yours. Is
this one
copy.
here. Yeah. Yes.
So it sounds like a minute ago you said to that guy that just changing one line of code to get 80% of the performance or whatever isn't good enough. But here you're saying use ChatGPT, it's faster, but
it won't be 80%. It won't be. I don't think it'll be 80% of performance.
Okay.
I think we have the actual profile for this particular example. You'll have to profile for your particular example, but in this one, there's actually more than 80%, I believe, if I remember correctly from last night when I was practicing.
With the ChatGPT version versus the equality here? Or?
No, with actually optimizing the code for ISO C++.
Okay.
Which is my point here. Write in standard C++ and compile, and code in a parallel first manner. That if you're going to take anything away from this presentation, I hope it's particularly that, as well as using our HPC SDK. So, and perfect. So that's exactly what I was going to get to here. So, if you take that code where we did the for each, and now we're just going to compile it for GPU here or for CPU. You're seeing here again, we're using it's 100% C++ code. You can use other compilers here like G++, but NVC++ of course supports compiling to GPUs. And you're seeing here, again, we're just changing the standard par flag. So there's no other code changes from what you saw. Okay, and so here's the performance difference here. Using just taking the OpenMP code and optimizing it for just changing it to standard C++, you got a 43% gain just from that. The additional thing is, of course, for GPUs, the gain is even further. And again, the idea here is code in parallel first. You know, again, the code wasn't serial first and then parallelism was added. You want to always have it parallel, okay? And so that's my lesson and takeaway here for this. And so moving, yes.
In both those cases, was that Black-Scholes body function a CPU function?
It was written in C++.
Okay.
Yeah. So here we go for this example here. So this example is broken in multiple parts. Again, we're going to use the same Black-Scholes routines inside. And so we're first going to look at this generate paths function here to model the results. And what you're seeing here with this array view, that's just like that 2D MD span. But you could, again, you can call it something else if you'd like. We're taking this path vec pointer. There you go. And it's a little small on my screen, apologies. So if my laser pointer is a little off, apologies there. And we're providing the number of paths and then this horizon to basically get this matrix out of that. And then what we're trying to emphasize here is, again, we're using our iota on the number of paths, as well as this for each, where this additional metadata from the MD span was provided so that you don't actually need to calculate that or pass it in yourself, which is a nice convenience. And then the other thing I want to show is, and I think this too is a little bit off here. So we're actually using the CPU random number generator here. We could have used Kuran's number generator or Thrust's number generator, but just to be strictly standard C++, without any other additional library changes, we wanted to just show that particularly here. So this is just one way that we just wanted to really, again, calculate a ton of paths to model these results. And so the baseline code here uses the same parallelism as the previous example one. Again, we're using for each here to parallelize over these options. Okay, also using iota. So we're using that same strategy that we were just saying. Now, walking over these paths is done on CPU. And so when you run this on GPU, there will be the number of paths, excuse me, where is it going? Yeah, the number of paths times this horizon kernel launches, which adds a little bit of, quite a bit of overhead actually. Lastly, as you see here, we're gonna transform and basically do a reduce on this and then calculate the maximum PNL here and an average to find the option with the highest profit and loss. And so the question here is really like, what if we parallelized across paths and options at once instead of doing this essential double for each, if you will? And so here we've moved these two path loops inside this this function, so we can parallelize across the independent paths. And so for one here in this part one here, I'm just also illustrating that again, that benefit of passing in spans and MD spans. They come with this metadata about their sizes, so you can use that rather than passing in the sizes. For here with two here, again, this we actually extract out that particular index in that for each. In later versions of C++, might come in C++ 26, you can actually use this like a Cartesian style product to actually automatically extract that out. Now, the key is if we're parallelizing, there's one key to this whole thing. If we're parallelizing across paths and across options, we actually could run into a little bit of a problem where we have a race condition where we're trying to calculate the same option at the same time. And so we use, you know, if you're trying to update the P&L for the same option in parallel, you could actually do that. And so you could actually run into that race condition. And so we use the atomic reference here to basically read, modify, and write to fix this. And essentially, you see the rest of that is essentially the same. And so why is this beneficial? So here's an insight
Just a
profile. Yeah.
second. So you're hiding the calculation of gamma and theta because they require random number generation, and you have to use a specific CPU, GPU compatible random number generation here. For example, I can't use that. You say calculate gamma and theta, but you don't actually calculate them.
Yeah, that's
So,
I'm just
so the reason is because you couldn't use the twister algorithm in the STD standard because that's CPU only, right?
So the idea here was we're not using GPU random number generators in this sample code.
So
Everything
I could
is
compile
exactly the
this and
same
run
because you're gonna, what's that?
So I could run this on a GPU even though that's a CPU random number generator? Okay, so that was the question. Okay, that's really neat then.
Yeah, this is why I think this is the coolest part of this whole presentation. So here's our insight system profile here. And if you did that double for each, as you saw in, you know, taking our learnings from example one, moving it over to example two, if you did that double for each, you actually end up with hundreds of these kernel launches, because again, that kernel launches are performed on the CPU. Well, they're initiated from the CPU using that. And so these kernel launches are actually expensive. And so what we did in this second example was actually merging them all into one kernel launch and moving over all the paths, giving you roughly a 5x speed up here. And so what I'm looking at in particularly here is you can actually see the GPU utilization in blue. You see like the spikes and then this red here. That's the GPU utilization. And then you see here in the second example, it's essentially all saturated here. And it's also a single kernel call. And then here are those individual kernel calls using the Insight systems where you can profile all that. Not to take I'm going to take a 30-second diversion to say, because I mentioned PyTorch earlier, PyTorch also supports in its API, you can do NVTX ranges. So what that essentially means is if you're also trying to profile PyTorch code, you essentially can push and pop things for profiling particular functions, and then read that into Insight systems and look at that same profile as well. So that's part of the PyTorch API. Just take a look and just do PyTorch NVTX, and that'll pop up right away in a quick search. All right, so to actually look at the performance results and address, essentially, you'll see your question here. We're baselining here to that serial paths here for this this parallel this P&L example here, and as you see here, when we did the for each on CPU, we actually we do see about a 38% speed up. And then on GPU, that same equivalent serial paths was faster than the 64-core processor. And then if you implemented this this parallel paths, excuse me, so this parallel paths was this one with this atomic reference, you see an even greater speed up. And so the lesson here, as I said earlier, is think in a parallel fashion first, expose more parallelism. If you have your code in C++ 17 or newer, take advantage of those particular newer APIs because they can provide some productivity enhancements or usability benefits if that's what you prefer. And compile, use the NVC C++ compiler to compile your particular architecture. Now, there is a cost to some of this synchrony. And so this kind of illustrates the inefficiency we saw in the previous example where lots of small kernel launches were bringing a significant overhead. So we're baselining to relative to a CUDA example here. And then with CUDA, we're actually solving this because CUDA can actually do asynchronous launches. So we can enqueue the work and wait once. But with C++ parallelism, we do sync with every call. But this is aiming to improve further. So with that syncing with every call, that's why we made one call essentially of that kernel and did all of that work and saw that benefit that essentially approaches that. And so this gets even better with C++ 26, which has that senders and receivers proposal. That'll provide a way to essentially provide an execution graph that includes all of the work. And you can launch it asynchronously and wait once for the results. And so you see how you can improve over that. And so in our simple performance benchmark, it resulted in essentially matching CUDA performance by removing the launch and sync overhead. And so that's another a benefit for the senders and receivers, which is coming. So there's actually preview support in our HPC SDK that you can use if you want to explore this a little bit further. And so this senders and receivers, as I highlighted a little bit earlier, unlocks a ton of possibilities. Again, you can write code once, you can build it to run on CPU or GPU, and you can already achieve this with what I showed so far. But senders and receivers is essentially a standardized way to make things asynchronous, and that has a lot of advantages for performance. As I highlighted our Grace Hopper architecture, you essentially have one piece of silicon with a GPU and a CPU connected on it at 900 gigabytes per second interconnect between both. And that chip has roughly 600 or so gigabytes of memory on that particular chip. And so you can see how having the CPU and GPU so tightly coupled together with senders and receivers can actually yield some new paradigms where you can run things on GPU and things on CPU asynchronously. And so this could be especially interesting, as I said. This standard exec library is available on GitHub. It's free. It's also included in the HPC SDK. And this was a GTC session. NVIDIA has a GPU technology conference annually. This is a particular GTC session that dives into a lot more detail into this idea. Okay, and so again, the cool idea here is you can express your task graph once. You can run it on that single scheduler for GPU or another one for CPU, or again, some hybrid schedule for both CPU and GPU. And so just to conclude this particular section, C++, as you know, it's a mature portable language here. C++ 17 provides that parallel library that gives you those building blocks for writing parallel first code. C++ 23 and 26 will give you new features, as we saw with senders and receivers and MD-SPAN. And our HPC SDK is freely available. It has all of these features here that we showed about with C++ compilers, debuggers, profilers, and as well as many different libraries. And again, you can use it, the HPC SDK, not just for GPUs. You can also use it on x86 CPUs, as well as ARM and open power. So you can get also those benefits as well. And lastly, I'm going to say it for the third time, write code that's parallel first to simplify code maintenance. You can, again, compile it to any platform you want and improve your productivity, whether or not you like ChatGPT. And so, modern processors, they have multiple cores. So just let's begin taking advantage of that full processor. Let's take advantage of all of it. So I have 13 minutes left. I can either end here or I can continue and talk about some large language model stuff. Yes.
So that, I mean, obviously you work for NVIDIA, but Intel has a software stack, one API. I'm not a GPU expert, but what do you have ideas on distinguishing features or like benefits or disadvantages to one stack of tools over the other?
So NVIDIA is really a full stack solution at the end of the day. It's not just software, it's not just hardware, it's both. Okay. And NVIDIA will work with you to help accelerate your particular application. All right. If you're facing issues, you have folks like Ronak you can reach out to and say, hey, I'm having this kind of issue. Can you work with that? And you can work with a lot of our CUDA developers. We have one of the largest communities for that kind of work. And so with GPUs from NVIDIA, you get that full benefit, okay? It's the hardware and it's all of the software in between that makes it work, right? Like we talked about communication libraries, all those things that need to work together to make that application work. Think about large language models, which we might get to, right? The amount of development that's involved to make the application level, like just even things like PyTorch, is enormous. You have to get matrix multiplication, just simple GPU kernels, right? You have to get communication libraries to work to talk between GPUs on a single node as well as multi-node and have that scale out. You have to work with storage as well. How are you going to fast, load data from storage directly through to the GPU, for example, for the maximum benefits? Because if you're going through that PCIe bus, you have to first load it into CPU RAM, then you have to copy it into GPU RAM. All right. And if you're if your storage is over the network, there's also an additional latency there. So there's a ton of those things that all need to work perfectly for your particular application. And NVIDIA is focused really on that whole ecosystem, not just on C++ coding for GPUs. And so I hope you didn't take that away. Really, it's that whole ecosystem of in that particular SDK where everything is designed to work together. Right. So if you're just more, coding in PyTorch and you download the container, you don't have to think about the dependencies involved in there. If you're going to do a multi-GPU training with using PyTorch, you don't have to think about how do my GPUs talk to each other and how am I going to do my all reduce or other kinds of functions. Or even if you're going to do something more advanced, like actually do compute in the network, where you don't have to do all reduce just by having 1,000 GPUs go onto one GPU and then sending the results back. You can actually do it on the network itself. All right, and so that's where NVIDIA is really investing its time to try to make that whole ecosystem experience more seamless. Okay, does that answer your question?
But we can talk afterwards.
Okay, if it doesn't, we can talk afterwards. I mean, again, I'm trying to highlight that you're.
Their hand for Fortran and options, so I know virtually nothing about GPUs. But arguably, Intel is okay. I mean, I have to modernize my own scientific programming. I have an option to pick, NVIDIA tools. There's the competing Intel One API. If I didn't know much about either, arguably Intel is a software and hardware company. NVIDIA is a software and hardware company. If I have to pick, is there a distinguishing feature between the two sets of tools that could help me pick? I mean, probably a lot of people are running NVIDIA GPUs with Intel processors. So they have to talk to each other, and it's probably in both companies' best interest to make that easy.
Correct.
Right. So are there better tools for one API for doing some set of things, or are there better tools for NVIDIA in the NVIDIA software stack that are better suited to certain tasks?
Yeah,
I mean,
sure.
I'm not trying to like, I don't know anything, so I have no horse in this
Yeah,
race.
no, the short answer is that, again, for things like option pricing, it's a hugely parallel problem, and the CUDA tools are simply more mature. It's been around a lot longer. We've thought about all of those things. You have everyone tuning those kernels every single day, whereas the one API system has not been around long enough, so it's not nearly as mature. And they're not thinking, listen, a lot of our systems use Intel CPUs. I'm not trying to bash Intel, but and great company, of course, but you have to think about the right tool for the right job. And so if your job is using a lot of parallel workloads, that's where the CUDA ecosystem shines. We could talk about it a little more later, and excited to kind of hear what your particular application is. All right. Yeah.
On the profiling system, do I need to like write the API into what I saw? I'm like one of these brain rotten people that use JAX.
We actually have a container for JAX.
But like, do I need to like change my program such that like emits certain information in my program to work with Insight or something, or Insight just like look at the GPU and figure out what the traffics are?
So Insight with JAX, that's actually one that I have not encountered before.
That's fine.
So presumably, yeah, I don't know if the JAX API has the like those NVTX ranges that you can include in there. If you can, then yes. My thinking would be yes, that they have that within JAX. But yeah, would recommend the JAX container that we have for GPU support. So I can spend. Yes.
So at the beginning, you mentioned these 5 levels of plugging NVIDIA software into whatever you're working on. So my question is, could you do more than one at a time? In the sense that if I'm writing something and I want to do the ISO C++, but on top, I want to write it on top of something that I already have, and I want to use OpenACC to kind of replace my OMP pragmas with, different quote unquote decorators. Is that something that will play nicely together, or do you just have to pick one?
Yes. Now you probably when you're compiling that one file, you don't want to mix, but yes, I mean if you have other files that are using OpenMP or OpenACC, yeah, it will play. Nice. Yeah. Okay. All right. I can briefly talk about this in 5 minutes. Kind of give some insights into large language models. Nowadays, a lot of my work is focused on large language models here and beyond. This is definitely a more of a twist towards what I do in financial services, but what we're seeing is that large language models are transforming the industry, not just the financial services and FSI industry, but other industries, and it's providing more accurate and predictive models. You already know that large language models like ChatGPT can be used for translation, text summarization, and sentiment analysis, but there's tons of other use cases where these finance-like large language models like Bloomberg GPT that I was involved with can be used to analyze financial data like news, et cetera, and use those sentiment scores to help find additional trading signals. These things can be, of course, used to generate new insights, trends, and even produce particular forecasts. NVIDIA, we actually have a library called Megatron. It's supposed to be a big, bad Megatron, but big and beefy in that sense. So it's our framework for training the world's largest transformer models. There's some papers in GitHub on that. It's also for free. And we also have containers for that use, that we have something called neural modules, which use Megatron under the hood for doing distributed compute. A lot of those communication libraries are in there to work seamless. And so we've trained 530 billion parameter models on this, even down to much smaller models, even for single GPUs. So it's everything ranging from, one GPU over to probably tens of thousands of GPUs. Megatron is incorporated into every single large language model framework that you've heard about. So you may have heard of Hugging Face, you may have heard of DeepSpeed or some of these other ones. It's incorporated. That code is already incorporated in there. Of course, in a number of AI startups that NVIDIA works with, as well as a number of apps that are trying to use it to enhance or incorporate new capabilities into their particular products. And so transformer models are used for a number of domains. You may have certainly see them for like text, but there's also image, audio, and as well as multimodal. So combining essentially multiple different domains together, speech, audio, text as well together for a particular task. We're seeing that in general, the model sizes, the larger the model, the more accurate it gets. Some of the folks here in the audience may have heard about Llama 2, where they have smaller models just trained with a lot more data. And while that's technically true, if you have a larger model trained on more data, you will still get more accurate. So that's something that we're seeing. And this flexibility can also make it well suited for a number of application domains, including tabular data, synthesizing tabular data instead of text. So tabular data is inherently structured instead of generating unstructured text. There was something that came up in one of our emails, Dan, where fine tuning came up as something. And so I wanted to highlight a couple different aspects of fine tuning, because there's some things that you're seeing in the media, et cetera, where there might be some inaccurate terms being used. And so for a particular large language model training you might be doing, there's varying levels of accuracy as well as compute for that particular investment. So starting from prompt engineering, which is essentially taking a large language model and tweaking the text a little bit and saying, oh, how can I ask it in this particular way or that particular way to get a particular output, like tweak my resume or something like that. Again, there's a number of particular techniques and why you'd want to do that. And that's like the least investment. And then next on that list is prompt learning, or which uses techniques like p-tuning, and these actually can add a couple of trainable neural net layers to the model to tune that model. And then there's techniques called parameter efficient fine tuning, or PEFT, which use techniques like LoRa, or low rank adaptation, for essentially doing these, adding these low rank matrices that get trained to an already trained model and enhancing that with your own data. So if you're using that for a particular application. And then lastly, you could do fine tuning, which you're essentially adjusting all of your weights for some downstream task. And so I know we have a minute left, but I want to leave you with that. And briefly, I'm going to mention that these large language models are really becoming quite interesting for a number of tasks. We actually use this for actually forecasting inflation. Inflation is obviously a big topic. We could do conditional generation here. We actually take in tabular data, and here's an example of where we forecasted inflation here, capturing the drop when COVID occurred, as well as the subsequent increase in inflation nearing 8.5% or so that we had in 2022. So we're seeing some interesting trends, and we believe that it can be an interesting additional tool in the toolbox. So you already have your techniques that you're using, fine. You have 50 different techniques, make this the 51st technique to consider exploring, and whether you're going to ensemble it or use it as just another technique for your particular application. And so with that being said, I'm out of time. Thank you very much for having me, and appreciate it. Thank you very much.